Hello everyone! In this video we will continue to examine topic 1.3, vectors and scalars, and in particular we will discuss the decomposition of vectors. Alright, so an important thing to be able to do algebraically is what is called decomposing a vector. Okay, decomposing a vector. So we have already discussed what the process is for taking two vectors at right angles and adding them. But often what we're going to do actually is take a general vector in any direction and say how much of it is in the horizontal direction and how much of it is in the vertical direction. That is, we're going to decompose it along the horizontal and vertical directions. We're basically undoing this process here, right? In this process, we took two vectors at right angles in order to say what was going on with the sum of those two vectors. And now what we're doing is basically starting in the other side and saying, okay, which two vectors sort of compose my original vector? So if I start with C, what are vectors B and A? Okay, that's the general process we're undergoing. And we're going to use, just as before, right triangle trigonometry. But conceptually, here's what's happening. We've got a vector with a certain length in a certain direction, and we're really asking for this vector, how much of it, if it's diagonal and to the up, how much of it is up, and how much of it is to the right. Okay, this process is known as decomposing the vector along the horizontal and vertical axes. It's worth noting, we'll see later, you don't just have the ability to decompose a vector along horizontal and vertical. As it turns out, you can decompose a vector along any axes you want. But we'll cross that bridge when we come to it. So let's start with this one, all right? First thing to recognize is that the side length up over here in relation to the original vector is just the length of that first vector times sine of theta. Okay, and that's just using the definition of sine theta. Similarly, the length of the horizontal component of vector A is just going to be the length of the original vector times cosine theta. And we'll often write these components as AY and AX. This is the Y component of vector A. This is the X component of vector A. So, for example, if vector A is 5 meters per second and it is at an angle of 30 degrees, then AX would be 5 cosine 30 is 4, and really I should have a unit on this, so 4 meters per second. It's going to quickly add that, and 3 meters per second for the Y component or the vertical component. Right? I will flip back and forth between X and Y and vertical and horizontal, in part because sometimes the vertical component might be an X component. So we got to be a little bit careful about that. But just for this purposes of this discussion, Y means vertical, X means horizontal. What this allows you to do, this vector decomposition, is as you'll see, it allows you to add vectors algebraically without pulling out a ruler and protractor. But the other thing it will allow you to do is represent A in different ways. So this right here, the norm of A is equal to 5 meters per second at an angle of 30 degrees relative to the horizontal. That's our traditional representation of vector A. But what you can do, actually, is just specify the two components of A as another way of giving the value of A. Again, I should probably have units on these quantities here. And that can be written in this particular form. We won't often do this, but you'll see this in math a lot. So vector A can be written as the X component and the Y component of those vectors. If you've seen vectors in HL Math or in another class, you can also write it like this if you don't have the vertical space to write it out. This just says the vector A is equal to the X component in the X direction plus the Y component in the Y direction. So there's a weird sense in which you're telling people this vector by saying, well, it's the sum of this vector plus this vector. And that's perfectly good. So you'll see that happen. So take a look at this particular example and see if you can decompose the velocity vector shown.